Okay, hi, welcome back. This is my second video and we're going to be talking about Le Chatelier's principle and what happens to the position of equilibrium when we change the conditions of a reaction. So first of all, what do we mean by Le Chatelier's principle? Now I've written out the textbook definition at the top. If a system at equilibrium is disturbed, the equilibrium moves in the direction that tends to remove that disturbance. As another way of putting it, the position of equilibrium will shift so as to oppose that change. Now, I like to think of it like if it's a really cold day outside, you put on a hat and a scarf and gloves and a coat and wrap yourself up really warm, and then you go outside. So if you imagine that is a position of equilibrium, you and the weather are in a position of dynamic equilibrium there. Now, if the temperature was to go up, so if you increase that temperature, you would start to feel hot and you would oppose that change by removing some of the layers. So you would oppose the temperature rise by removing some of the layers to cool yourself down again. So that's kind of an analogy that I like to use. Now, what do we mean by the position of equilibrium? What we mean is, imagine this reaction again, this generic reaction A and B goes to C and D and back again. Now, the concentrations of reactants and products could be equal. It could be half of A and B and half of C and D. And in that case, the position of equilibrium would be in the middle. It could be the case. It's probably unlikely to be exactly in the middle, and it certainly isn't like that for all reactions. So sometimes you'll have a much higher concentration of your reactants, and that means the position of equilibrium lies over to the left. Or you could have a really high concentration of the products, and in that case the position of equilibrium lies over to the right. So by changing the conditions of the reaction, that position of equilibrium will shift. So if you imagine it like a balance, like scales, the position of that equilibrium will shift so as to counteract that change. Now, the three conditions you have to know about for this part of your syllabus is concentration, temperature and pressure, and I believe this is all GCSE recap for all of you. So let's talk about concentration first. Now, I've left out something here. Matt should be able to tell me. State symbols. So let's put them in. AQ, 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 and AQ. So we're talking about concentration, so we're talking about solutions. Now, if I was to increase the concentration of A or B, what's going to happen is you're going to add more particles of, say, A, just to make it easier to talk about. You're adding more particles of A, and therefore you're going to have more successful collisions, aren't you? So what's going to happen is you increase the concentration of A and B, the position of equilibrium will shift so as to oppose that change. So what's going to happen is you're going to make more of C and D. So you increase the concentration, of reactants, for example. The system will move to reduce the concentration of reactants, and it will do that by making more of C and D. It will be making more of the product. So the position of equilibrium shifts or shifts to the right. So you increase the concentration of the reactants, the position of equilibrium is going to shift to the right to make more products. Okay? Now, increasing the concentration of the reactants is going to be the same as if you decrease the concentration of the product. So if you start this reaction off it reaches equilibrium and you start to take away the C and D, take away the products because you need it for something, then that's the same thing as increasing the reactants here. So you remove the products here and you're going to start to make more of them. Again, that position will move to the right. Now, I want you to try to include these 3 bits of information in any answer you give, because quite often in the mark scheme, this part of the response is missed, and it quite often you get a whole mark for it. So make sure that you talk about, so you increase the concentration of the reactants, the system's going to move to reduce that concentration, or you can say the position of equilibrium will shift to oppose that change, and then state where that position of equilibrium is going to shift to. So if you were to increase the concentration of the products, the same thing would happen. The system would move to reduce the concentration of the products, and the only way it can do that is to make more of the reactant, so the position would shift to the left. Okay, now let's talk about temperature. I've actually got a proper reaction to talk about temperature. Which reaction do I have? Yeah, I'm going to give, so we've got 2SO2. I think I'm always going to give you the reactions in your textbook and your syllabus, because they're the ones I think you're probably likely to be asked about. So we've got that SO3. And the enthalpy change of the reaction is negative 197 kilojoules per mole. So we know about kilojoules per mole, we know about enthalpy change because we've already done that topic of enthalpy. And in energetics. Okay, so we've got this situation here, this reaction here. So we've got 2SO2 reacting with O2, forming 2 lots of SO3. And the enthalpy change is negative 197 kilojoules per mole. So what you should know is that negative means that the reaction is exothermic. Now that means that the reaction is exothermic in the forward direction. So forward is exothermic, and that means it gives out heat to the surroundings. Okay, and if a reaction is exothermic in one direction, it's going to be endothermic by the exact same amount in the opposite direction. Endothermic equals takes in heat. Okay? So you should be familiar with this. This again is GCSE stuff. It's also a recap of energetics as well. So you should be really, really familiar with this. So what's going to happen if we change the temperature? So the example we'll give is increased temperature. The system is going to oppose that change. So the position of equilibrium will shift to oppose that change. So what's going to happen is the system will absorb that heat to cool it down again. So system will absorb heat to oppose change, and the system will move, or the position of equilibrium will shift in the endothermic direction. Position POE, position of equilibrium, will shift to the left, in this case endothermic direction. Okay, so you've increased the temperature, so you've added heat to the system. The system is going to respond by opposing that change, and it will do that by absorbing the heat. And so the position of equilibrium will shift in the endothermic direction. In this case, that's the backwards reaction. So here, if you had a question that said, if you increase the temperature, what's going to be the effect on the yield? You say it will reduce the yield of SO3 because the system will, the position of equilibrium will shift in the endothermic direction to oppose that change. So you'll get less yield. Okay, I'll give you, have I got another example? I have got another example that I wanted to share with you, because you could easily be given another example. So we've got N2O4. We'll put a state symbol in for Matt, and we've got and the enthalpy change there is equal to 58 kilojoules per mole. So this reaction is endothermic in the forward direction. So we've got endothermic in the forward direction. So it absorbs heat in the forward direction, and then we've got exothermic in the backwards direction. So in this case, if we increase the temperature, so increase temperature, the system's going to oppose that by absorbing that heat. By absorbing heat. And it will move in the endothermic direction. POE shifts in endothermic direction. Direction, D-O-R-E, but you've missed my spelling, which in this case is to the right. Right, when you look at it, right, okay? So because the reaction is endothermic in the forward direction, and you know that because you've got a positive enthalpy change value, you increase the temperature, the system's going to oppose that change by absorbing that heat, and so the position of equilibrium will shift in the endothermic direction, which is to the right. Now, this is all the case vice versa as well. So if you decrease that temperature, then the system's going to oppose that change by giving out heat, and it will move in the exothermic direction. So everything's exactly the same the other way around, okay? And then finally, we've got pressure. So let's have a look at pressure. And again, this is all GCSE recap. So if you are feeling rusty on this, maybe you should just have a read of some of your books. So we've got our sulfur dioxide reaction again, and O2 gas is going to sulfur dioxide. Okay, now I'm not going to put an enthalpy change value there because we don't need to talk about that when we're talking about changing the pressure. So changing the pressure only applies to reactions in the gas phase, okay? So if you've got a reaction that's involving solutions and you're asked a question about pressure changes, it's not going to have an effect. So pressure is only going to have an effect when you've got a different number of moles. So we're talking about pressure, PR, pressure. Affects position of equilibrium only when number of moles on either side is different. unequal. So what's going to happen? You've got to imagine that increasing the pressure is basically has the same effect as increasing the concentration, because a pressure is a number of particles per unit volume. So if you increase the pressure, you're reducing the volume, so you're essentially increasing the concentration. So what's going to happen is increased pressure, imagine on this system, the system is going to oppose that change. System opposes change, and it will do that by shifting the position of equilibrium to the side with the fewest moles. By shifting POE to side with fewest moles. Because if you think about it, you increase the pressure, you're going to increase the concentration. So in order for the system to oppose that change, it's going to try and reduce that concentration. So it will shift, the position of equilibrium will shift to the side with the fewer moles. So in this case, we've got 1, 2, 3 moles this side, moles, 3, and this side we've got 2. So if you increase the pressure of this reaction, the position of equilibrium would shift to the right. Shift P, O, E, shift to right. And exactly the same if we reduce the pressure. So if we reduce the pressure in this reaction, the system's going to oppose that change by trying to increase the pressure or increase the concentration. So the position of equilibrium would move to the side with more moles. Okay? So just to recap, in this case we've got 3 moles this side, 2 moles that side. So 3 moles in the reactants, 2 moles in the products. If you increase the pressure, the system's going to oppose that change by trying to reduce the pressure again, so the position of equilibrium will shift to the right. Now I want to give you, these are 2 more examples that are in your textbooks, and they were little tricky ones, which you should, well, hopefully you'll see no problem. H2O, so we've got some steam and carbon monoxide gas. Just make sure that's all balanced, and it is. Okay, so the question asked what would happen to the position of equilibrium in this reaction if you were to increase the pressure, and the answer is nothing would happen to the position of equilibrium, because this side, moles, got 1, 2, this side I've got 1, 2. So you increase the pressure, nothing happens, because the number of moles are equal both sides. So nothing would happen if you increase the pressure. The system can't move to oppose that change. One thing I want to make clear in this video is that if you increase the concentration or the pressure or the temperature of any of the reactions that you're looking at, you will increase the rate of the reaction. So if you remember from the kinetics topic, all of these 3 conditions affect the rate of reaction, but the rate of reaction and the position of equilibrium are completely different. So whilst if you increase the temperature, you're going to increase the speed at which you reach the equilibrium. The same as if you increase the pressure, you're going to increase the speed at which you reach the equilibrium, but not necessarily the position. Okay, so my next video I'm going to come back and we'll go over some KC calculations, but that's it for this one. Okay, thanks.